welcome to our series of SPI lectures. So today we're going to look at transducer theory and resolutions. My name is Negedu Godwin. I'm your regular anchor. My appreciation and acknowledgement goes to these wonderful people who has contributed immensely to my knowledge. Now, what is a transducer? A transducer is any device that converts one form of energy into another form. An ultrasound transducer converts electrical energy to sound energy during transmission and sound energy into electrical energy during reception. Ultrasound transducer uses the piezoelectric effect to convert electrical energy into sound energy and converts back into electrical energy. Transducer crystals, or elements if you wish. So for the purpose of this class, we're going to be using elements and sometimes crystal interchangeably, that is one and the same thing. So transducers may be of two types depending on the number of piezoelectric crystals that is within it. So the first type is a single element and the second type is a multi-element. Now A mode, M mode, and static B mode scanners use a transducer with single elements. Old mechanical real-time systems also use a single piezoelectric crystal transducer. But we have arrays, and arrays use multi-element transducers that we generally call arrays. All modern electronic transducers are arrays, all modern. That contains an arrangement of multiple small piezoelectric crystal elements. So basically, there are multiple of them that are arranged in your probe. So piezoelectric effect, let's see how this works. Now this is a property of a certain material or element to create vibrations when voltage is applied to them, or when they are mechanically deformed. Now, piezoelectric in the Greek word means pressure electricity. So, piezoelectric effect is a material's ability to change from one form, to change from its form to energy and to another form of energy. So, changing from one form of energy to another form of energy. That's any material that has that ability is exhibiting the piezoelectric effect. It occurs when an electric field is applied to a piezoelectric material, which causes a change in the material's physical dimension. The physical change on that material then produces an electric field or vibration of the piezoelectric crystal in the transducer, this transducer is used in ultrasound to produce images. There are types of piezoelectric effect. There is the direct piezoelectric effect, there is the indirect piezoelectric effect. The direct piezoelectric effect is a form of an electrical charge on the surface of the crystal when pressure is applied. In the post-echo imaging, this effect occurs on reception when echoes return to the transducer and are converted into electrical signals. The indirect, or what you call the reverse piezoelectric effect, will occur during transmission of the sound. In response to an electrical voltage applied to the crystal undergoes mechanical deformations rapidly, and there's a rapid contraction and expansion that occurs. Now, this causes high-frequency mechanical pressure wave to propagate through the tissue in the form of ultrasound pulse. Let's look at piezoelectric materials. These materials change their shape and vibrations when voltage is applied to them, based on what I just explained. So their primary component is a crystal with a piezoelectric property. Remember piezoelectric property? Piezoelectric materials are found in two forms: natural and synthetic. Natural, you have the quartz, rochelle salt, tourmaline. These are natural occurring piezoelectric materials. Then the synthetic, which you may wish to call ceramic crystals, because that's what they are. These are lead zirconate, lead titanate, lead zirconate titanate, barium titanate, and the host of others. Another synthetic type of crystal is made of hard plastic, that is plastic polymers. Example of such is the polyvinyl difluoride. So these are synthetic piezoelectric crystals. So ceramic crystals are much more sensitive than natural crystals. They respond more easily to small electric signals and to weak echoes. So here you have the schematic diagram that shows you the skeleton of a probe. So we have the backing material, piezoelectric elements, the acoustic matching layer, and we will go into all that in the process of time. Piezoelectric crystal, let's look at the active elements. The piezoelectric crystals or active element is located at the face of the transducer. It is flat. It is a flat circular disc with an approximate diameter of 6 to 19 millimeter and a thickness of 0.2 to 2 millimeter. Now this crystal can generate ultrasound pulses when applied with a voltage. They act as receivers of returning echoes, and they generate electricity or voltage in response to received echo pressure. So this image is to show you the back and front that goes with these crystals. From electrical energy, there's a deformation that goes on in the crystal, then it produces pulse waves, mechanical energy. Then from the mechanical energy, on receiving the echo, goes through the crystal, which change its form or configuration to produce voltage, electrical energy. To produce ultrasound, the piezoelectric crystal undergoes the following process. Let's see how this happens step by step. Within the crystal, there are dipoles, molecules with positive and negative charge ends. These are what dipoles are. A high voltage current is applied to either end of the crystal by the electrode, which causes it to expand. The polarity of the applied voltage is then reversed, and the crystal becomes smaller in size. The electrodes have positive and negative terminals, which give and collects electricity. When an electric field is applied to the crystal, it causes the dipoles to realign, which causes change in the dimension of the crystal. The crystal thickness increases when the voltage is applied. So remember, voltage being applied and sound being received is causing a pressure, a contraction and expansion of this crystal. And again, when the reverse polarity is applied, the crystal thickness decreases. This process of change in crystal thickness results in compression and refraction. The crystal will expand and contract at the same frequency as the electric signal operates. So the same frequency, the electricity you're applying is the same frequency with which the crystal will contract and expand. The greater the amplitude of the returning echo, the greater the degree of deformity that occurs in the crystal, and the higher the voltage that will be produced. These voltages are then converted into shades of gray, that's black and white, in the normal 2D grayscale ultrasound, which make up the final ultrasound image. Let's look at the polarization of this system. Now remember that polarization is a process of geometrically aligning the dipoles of a crystal in order to give them piezoelectric property. Natural piezoelectric elements have natural piezoelectric properties. But the synthetic crystals, on the other hand, must be polarized in order to possess piezoelectricity. After the crystal is formed and shaped, it is heated in an oil bath at a very high temperature in the presence of a strong electric field. That's how synthetic PZTs are made. So at the high temperature, the dipoles are free to move around. While it's in this state of relative freedom, an electrostatic field is applied to the crystal, which causes the dipoles to align with their negative ends towards the positive side of the electric field and vice versa. While still under the influence of strong electric field, the temperature of the bath is gradually lowered. So as room temperature is reached, the dipoles become fixed on the crystal, and that crystal is polarized. Now remember Curie in your regular physics. So there is Curie point or Curie temperature. So what is Curie temperature? What is Curie point? Curie point is the temperature at which polarization in a crystal is lost. If the dipoles are disordered, the crystal is in a state of depolarization and does not possess piezoelectric properties. Heating a piezoelectric crystal above the Curie temperature renders the crystal useless. Now, if the synthetic crystal is reheated without an electric field present, it will lose its polarization permanently. Therefore, a transducer should never be heated or autoclaved. Should the transducer need to be sterilized, this should be done using cold gas sterilization process. Another simple method of maintaining a sterile field is to enclose this transducer and the cable within a sterile sheet. So the approximate Curie point or temperature for several crystals is listed in this picture. Here you have the quartz, the Curie point for quartz, Curie point for barium titanate, the PZT4 Curie point and PZT5A Curie point, and it's listed there. I'm sure it will help you. And this image shows another schematic diagram of a regular probe, the skeleton, dissected skeleton. So you see what the probe contains. So in the probe, you have the backing material, we have the transducer, plastic membrane, and all that. So let's look at some of these components one after the other and how they apply. So let's start with damping material, or what we call backing material. It is a material usually made up of plastic and metal powder. Actually, it's epoxy resin with tungsten, and is located or bonded to the back of the crystal. It acts to limit the ringing of the crystal by damping or absorbing the vibrations. So it shortens the pulse duration and the spatial pulse length. All that we'll discuss in the process. The shorter the pulse duration and the spatial pulse length, the better the image quality. So damping material acts to improve the image quality. So we'll look at these parameters in other lectures, but this will inform you ahead of time what damping material does, so that as you construct your device, you're able to know what plays what, the role of every material in your device. What's the function of a damping material? I've said it shortens the spatial pulse length and the pulse duration, which improves axial resolution. And that means it improves image quality. It increases the bandwidth, that is the range of frequency within the pulse. It increases it. It decreases the quality factor, the Q factor of the transducer. So for imaging ultrasound, we require actually a low Q factor for these ultrasound transducers. It also decreases the sensitivity of a transducer to reflect echoes. It dampens, dampening will allow crystals to vibrate for like 2 to 3 cycles, which produce short pulses. But without a damping block, the crystal will vibrate many cycles, which will produce a very long pulse. The other material in your transducer or probe is the matching layer. So what does the matching layer do? So let's look at it. The acoustic impedance and mismatch between the transducer and the patient's skin is very high. This produces a high percentage of beam reflection and allows very little beam transmission that is required for ultrasound imaging. This phenomenon limits the performance of ultrasound system in imaging the body tissue. So to overcome this problem, a matching layer is incorporated to the face of the transducer, which allows smoother transmission of ultrasound beam into the body tissue. Thus, it increases the sensitivity of the ultrasound system. Now, this is achieved by reducing the acoustic impedance mismatch between the transducer face and the skin interface. The matching layer is made up of material which has acoustic impedance that is between those of the crystal and the skin. It facilitates more sound transmission between the crystal and the skin by reducing the percentage of initial ultrasound reflection between the crystal skin interface. So the matching layer also improves the detection of weak returning echoes, which are very weak due to attenuation that occurs to the beam previously. So here we have an image of the matching layer. Its location in the whole architecture of your probe. So let's look at 1/4 wavelength technology. All these are applied to give the kind of quality of image. So what does 1/4 wavelength technology mean? What does it do? So here, manufacturers found that the most efficient thickness for matching layer is 1/4 wavelength of the ultrasound pulse, and it's called quarter wavelength technology. The quarter wavelength matching layer is used for one frequency only. The ultrasound beam emits a main frequency as well as a spectrum of other frequencies. So manufacturers are now producing transducer with multiple matching layers to deal with the spectrum of frequency that is emitted. So the multiple of it reduce the wavelength to 1/4, so that you have all those frequencies being handled or dealt with in the background, giving a good quality image. Coupling gel, our famous gel. Everybody uses a gel, so let's look at it. Coupling gel, or what you call acoustic gel, has acoustic impedance between those of the matching layer and the skin. What did you notice? Everything in between the transducer itself and the skin, patient's skin, has acoustic impedance that is in between these two materials, the skin and the transducer. Now, the acoustic gel has the impedance between the matching layer and the skin. All for what? To help transmit sound into the patient body. This is being used between the transducer and the skin to further minimize the acoustic impedance mismatch between the transducer and the skin interface, to further facilitate ultrasound transmission into the body tissue. Now, electrodes or wires. So when you carry your machine, you dismantle the probe, you look at the skeleton, you see lots of wires. So these electrical contacts that is working, they work in two ways. They work to excite the crystal and produce ultrasound pulse, and they act to receive echoes and convert it into voltage. There is a material called the filler material, and they are added onto the face of the transducer to maintain a smooth surface for contact, especially when the crystal and the matching layer are curved for beam focusing. Then you carry your regular probe, look on the surface. That gray, blue, or black surface, that material is actually the filler material. Waterproof plastic case and insulator. So what encapsulates all these components is the plastic case or the insulator. It's usually made up of plastic hermetically sealed with an important electrical insulation. It protects the fragile components of the transducer and thus accommodates rough handling. Protects the patient and the operator from electrical shock. So anytime you see a crack on your probe, please take it seriously to avoid shock. These are precautionary measures. It prevents electrical noise from interfering with the transducer performance. Now, transducer frequency. The frequency produced by the crystal of a transducer is different for the continuous wave ultrasound and the pulse wave ultrasound. In continuous wave ultrasound, the frequency is determined by electrical frequency of the excitation voltage that is applied to the active element by the ultrasound. The frequency of the continuous wave ultrasound is identical to that of a continuous electrical signal that drives the crystal. In other words, 50 megahertz electrical frequency will produce 50 megahertz sound frequency. That's what happens in the continuous wave. But in the pulse wave ultrasound, the frequency of the sound is determined by the characteristics of the crystal by a combination of two factors: thickness of the crystal, the velocity of sound in the crystal medium. So the thinner the crystal, the higher the frequency. The thicker the crystal, the lower the frequency. Velocity of a sound in crystal is basically 4 to 6 millimeter microsecond. It is 3 to 4 times faster than that of soft tissue. The shape of crystal or the crystal geometry also determines the beam profile. We'll discuss that in other lectures. Depending on the transducer type, it may be spherical, rectangular, or square. It may either be flat in an unfocused transducer or curved for focused transducer. Resonance frequency. At ultrasound transducer, there is this design that maximizes the sensitivity to a specific frequency. This optimal frequency is called the transducer's resonance frequency. Resonating frequency is the operating frequency of a transducer. The resonant frequency is the natural frequency of the transducer, or what you call the fundamental frequency. It is the frequency that will have the greatest amplitude. For example, this image shows you the equation for resonant frequency. There you have FO in megahertz, C in meter over 2 width. So where FO means resonant or operating frequency, crystal material, cm, which is measured in millimeter microsecond. Then 2W, that is width, means 2 times the thickness of the crystal in mm. So resonating or operating frequency is determined by crystal thickness. The thinner the crystal, the higher the frequency. The thicker the crystal, the lower the frequency. Frequency of a pulse wave transducer is inversely related to the thickness. Now, crystal materials propagation speed, here's the relationship. The higher the speed, the higher the frequency. The lower the speed, the lower the frequency. Now, frequency of pulse wave transducer is directly related to the velocity of sound in crystal. Transducers that emit high frequency of sound wave are made of very thin crystal with very high propagation speed. That's how high frequency transducers or probes are made. At lowest frequency transducer, they have thick crystal with slow propagation speed. Now, there is such thing as the 1/2 the wavelength technology. So half wavelength technology or 1/2 wavelength technology. The thickness of the crystal is half the wavelength of sound traveling in the crystal. It means that to make a specific resonance frequency, the crystal needs to be cut to a thickness equal to the 1/2 of the wavelength of that frequency based on the speed of sound in the crystal material. For example, let's say we wanted to create a crystal with a resonance frequency of 4 megahertz. Using the wave equation and the speed of sound in the crystal, which will be 4 millimeter microsecond, we can determine the required thickness by using the wavelength, wavelength, which is speed of sound over frequency. We already know what that is in the question. So wavelength here will be 4 megahertz. Then the crystal thickness will be half of that. Yeah, so remember, the thinner the crystal, the higher the frequency. Bandwidth. Because of the effect of the damping material we discussed earlier at the back of the crystal, an image transducer does not emit a sound pulse that is composed of pure single frequency. Rather, the pulse contains a range of frequencies below and above the resonating frequency on either side of the resonance frequency. Now, this range of frequency is also known as frequency bandwidth. In this image, you look at what we call frequency bandwidth, and it's the difference between the highest and the lowest. Bandwidth is actually the difference between the highest and the lowest frequency that is found in a pulse. For example, if the resonance frequency is 4 megahertz, like we discussed earlier, the transducer might also produce frequency that range from 3 to 5 megahertz. So this range of frequency is known as the frequency bandwidth. In this example, the center frequency is 4 megahertz, like we mentioned, and the bandwidth is 2 megahertz. That is the difference between 5 megahertz and 3 megahertz, as you see on the graph. So the narrower the bandwidth, the more exact the frequency emitted by the transducer. The damping material tends to increase the bandwidth. So in diagnostic ultrasound, we want to use very short pulse of ultrasound because short pulses give the best resolution. We'll discuss all that in other lectures. The process of damping increases the range of frequency. That is, it increases bandwidth in sound pulse. Damping also produces shorter pulse. The shorter the pulse, the wider the bandwidth. The shorter the pulse, the higher the image quality. The higher the bandwidth, the better the quality. Don't forget. So a 5 megahertz transducer actually emits a range of pulse that composes of 3.5 megahertz to 6.5 megahertz in its bandwidth. So the center frequency is actually the resonating frequency, is 5 in this case, and the bandwidth is 3 megahertz when you take the difference. That's the difference between 6.5 megahertz and 3.5 megahertz in the bandwidth. Q factor, otherwise called quality factor. So this represents the ability of a transducer to emit clean ultrasound pulse with a narrow bandwidth. It describes the ability to transmit and receive ultrasound energy. Now this is the equation for the Q factor, which is operating frequency over bandwidth. So low Q factor transducers are used in diagnostic imaging ultrasound because they can create short pulse which produce high quality. They can have wide bandwidth. They are better receiver. They receive wide range of returning frequencies. Hence, the imaging transducer are all having wide bandwidth with low Q factor. But in high Q factor, the transducers are used for continuous wave Doppler image ultrasound and also in therapeutic transducers where no image quality is required, rather than better transmission that is needed in such case, because they can create long pulse, narrow bandwidth, and they are better transmitters. So you may want to ask yourself, what is the Q factor of a 3 megahertz transducer with 1 megahertz bandwidth? The answer is 3. Electrical shields and noise, very important for device producers. Look at electrical shields and noise. The electrical shield is an isolation barrier that serves to pick up unwanted stray signals, which we refer to as noise. The unwanted signals are sent to the ground through the earthing cord. Having said that, let's look at signal to noise ratio, which is very important. Once an echo returns to the transducer, it generates an electric signal containing information about the reflector. This signal must be distinguished from unwanted signal, which is called noise. We distinguish that signal from the noise. Now, noise does not contain echo information from the reflector and contributes to the degradation of the ultrasound image by producing artifacts. Noise must be eliminated or suppressed by the ultrasound machine. So a measure of ultrasound system's ability to distinguish echo information from noise is the signal to noise ratio. So this signal to noise ratio, there's a difference between different machines. Low end, high end machines have different signal to noise ratio. For example, let's say example of signal to noise ratio, we can have 10 to 1 or 20 to 1. So the bigger the number, the better the quality. So 20 to 1 signal to noise ratio is far better than 10 to 1 signal to noise ratio. This image shows you multi-hertz transducer, or what we call the broad bandwidth transducer. Remember in the old days, using a single crystal transducer, the operating frequency was fixed. So in order to change the frequency, one will need to change the transducer. Yeah. Now we use a very wide bandwidth array transducers, which allow us to electronically change frequencies without changing the transducers. So on the same transducer, you can just punch your keypad and you change the frequency in current machines. This is called multi-hertz or broad bandwidth transducers. The pulsar can electronically force the crystal to vibrate at a frequency other than its natural frequency. Okay, for example, using a broadband 8 to 12 megahertz transducer, the operator can use the frequency of 9, 10, and 11 megahertz. That is, the user has the ability to select multiple center frequency on a single transducer. And that is pretty cool. It makes life for the operator easy. Harmonic frequencies. These are frequencies that are multiples of the resonance. Remember, resonance frequency is actually operating frequency. Yeah. So, for example, if the resonance frequency is 3, the second harmonic is 6 megahertz. The third harmonic is 9 megahertz. Harmonic frequencies are generated in tissue. With higher harmonic frequency, the system can produce images that have less noise and clutter, improving the image quality. It is particularly helpful when imaging larger patients who have increased attenuation. So let's look at image production factor. Sound beam anatomy, beam profile. Let's look at that. A sound beam is shaped like an hourglass. As sound travels, the width of the sound beam changes. At its starting point, it is exactly the same size as the diameter of the face of the transducer. The beam gets progressively narrowed until it reaches the smallest diameter, then it diverges. A sound beam can be broken into the following components on this picture: the near field, the focal zone, and the far field. Focus is that point where the diameter of the beam is at minimum. It is the smallest diameter in the beam, and it's also called focal point, as you see in that image. Now, the focal length or near zone length is the distance from the transducer face to the focal point or the focus, where the beam reaches its smallest diameter. So from the face of the transducer to that point where it reaches its focus, that is the near zone length. Near zone length, near zone field, or Fresnel zone are all one and the same thing we're talking about. The region between the transducer and the focus is all this word, you can use it as the same thing. Near zone field, Fresnel zone. But far zone, far field, Fraunhofer's zone, these are regions that are deeper than the near zone. So the focus zone is the region surrounding the focus that generally has narrower beam. It is the middle of the field, the mid area of the image. One of the important factors that affects image detail or image quality is the beam shape. The narrower the beam, the beam width, the better the image detail. The image quality is at its best the image quality is at best in the best depths where the beam is narrowest. So where the beam becomes narrowest, that's where you have the focus, and that's where your best quality image is formed. Well, so what are the factors that could affect beam profile? When discussing ultrasound beam, we must first distinguish between unfocused beam and focused beam. Clinically, we always use focused beams. However, when discussing general principles of beam formation, we start by looking at unfocused beams, which we call natural beam. There are two main factors that determines the profile of an unfocused beam, and they are the diameter of the crystal and the frequency. In an unfocused beam, the narrowest part of the beam is called the transition point. In a focused beam, the narrowest part of the beam is called the focal point. Let's take a quick peek at unfocused beam. The sound beam produced by an unfocused transducer has some specific characteristics and are same for both continuous wave and pulse wave transducers. An unfocused sound beam is divided into two distinct regions. The near field, which you also call near field zone or Fresnel zone, extends from the transducer face to the transition point, that is the narrowest point, and is characterized by beam convergence, and a natural focus. The distance from the transducer face to the transition point is called one near field length. So far field or far zone or Fraunhofer zone is the portion of the beam beyond the transition point and is characterized by beam divergence and progressive widening of the beam. So near field length, focal length, let's quickly look at what that is. So near field length is the distance from the transducer space, like we said before, to the focal point, where the beam reaches its smallest diameter. The longer the near field length, the longer the narrower portion of the beam will be, which is desirable for better resolution. The near field length is determined by two parameters, that is the diameter of the transducer and the transducer frequency. So this equation represents the near field length. It can be seen from that equation that near field length is directly proportional to the frequency of the transducer, is directly proportional to the diameter squared of the transducer. If the transducer frequency or diameter is increased, the near field length will be increased. If just one of these parameters change, the near field length will be changed. So large diameter transducer produce beam with deep focus. Small diameter transducer produce beam with shallow focus. High frequency transducers produce a deep focus. Low frequency transducer produce beams with shallow focus. We'll see some of these effects as we go into other specialty to discuss diagnostic scanning. For an unfocused transducer operating in a continuous mode, at the end of the near field, the beam diameter is half of the transducer's diameter. So at 2 near field lengths, the beam diameter equals the transducer's diameter. The same for this, we talk about the far zone, far field, and Fraunhofer's being the same thing. So this is actually the region that is deeper than the near field, but we do not measure the length of the far field. We should know the following things about the far field. It is a region of beam divergence. Being a region of beam divergence, the beam intensity is reduced because the beam area is increased. Being a region of beam divergence, the beam becomes wider and wider, which makes lateral resolution worse and worse. The factor that determines the beam divergence in far field are the same two factors that determines the length of the near field, right? Crystal diameter and the frequency. An increase in crystal diameter and or frequency will reduce the beam divergence in the far field. In the far field, at a distance equal to 1 near zone length from the transition point, the beam diameter is equal to the crystal diameter. The usable length of an unfocused beam extends from the transducer face for a distance equal to 2 near field of the length. That's what is usable for the far field. Image resolution is better in the near field area over the far field area because the beam divergence in the far field, so as it diverges, quality of image becomes poor. Remember, the best image is at the point of like, share, subscribe for more free SPIs. And please also subscribe to our paid classes by sending me a DM or a mail to sonoeyesdiagnostics@gmail.com or WhatsApp me at +234 9019 144 175. I'll see you in the next issue. Keep learning ultrasound.